Welcome back, everybody. In this video we're going to learn about a new term, but it's actually an old term, or it's a term that we've learned about before, but we're going to be using it in a completely different way. The term is called tangent. We're going to be learning about lines that are tangent to a circle. This tangent is completely different than the trigonometry tangent we've talked about from the SOHCAHTOA stuff. But let's take a look and let's think about what it means. So first I have a question for you. If a line was randomly drawn on the same plane as this circle here, how many times would that line intersect the circle? So you can imagine the screen that you're looking at is the plane, and if I were to put a line on this screen somewhere in a random place, how many times would it intersect this circle? And so if you think about that for a second, you would probably come up with a couple answers, right? If it was randomly placed, there's a chance that that line would never intersect the circle. So let's draw a line like that. Let's draw a line that does not intersect the circle at all, right? So this line here would have no point of intersection on the circle. But then, of course, I could draw the line so that it does intersect the circle, and maybe it intersects the circle 2 times. So maybe a line like this would actually have 2 points of intersection. We can see one here we'll call point A, one here we'll call point B. But is that the only 2 possibilities, that we would have a line that would never intersect the circle, and then we'd have a line that would intersect the circle twice? Some people might say, well, what if it was a line that looked maybe like the one I'm about to draw here? What if it was a line that looked like this? Would that intersect the circle in only one place? Would this point right here be the only point of intersection? And the answer, of course, would be no, because we know that lines are going to continue going in both directions. So even though as it continues going off in this direction, kind of to the right on your screen, it would never hit the circle again. When it continues going towards the left, it's going to hit the circle again right here. So this line would actually still have 2 points of intersection, just like the purple one down here. So it would almost maybe seem that this is the only 2 possibilities. It would either never hit the line, or it hit the line in 2 places, like either the purple or the red line. But there is actually a way that we could draw a line so that it would only touch the circle in one place. The line would look a little bit like this. Let me see if I can draw one. It would look maybe a little bit like this. Let's see. About like that. This line here, it's only touching the circle in this one spot right here. I'll label it as point D. It's only touching the circle in one spot. It's kind of coming up through here, and it's just grazing the circle as it goes by, only touching it in that one single point. And that is the kind of line that we're going to be looking a lot at in this video. That line there is called a tangent line. So let's define a tangent line real quick. A tangent line is going to be any line that's in the plane of a circle and that intersects the circle in exactly one point, right? So here's another example of a tangent line. Line QR here would be tangent to circle P. We would say that that line is tangent to circle P, and that one point where it intersects is our point of tangency. So we could label that point there. We could say that that is a point of tangency. And again, one of the phrases we might see on a picture like this is we might see some kind of description that says that line QR is tangent to circle P. Right, that might be a descriptor of what's happening here. And point Q would be that point of tangency. Now, off of that definition, we're going to have a couple theorems. The first one says that if line AB is tangent to circle C at point P, so in other words, if point P is our point of tangency, then line AB is perpendicular to segment CP. And so that's what the theorem says, but I like to maybe try and rephrase that a little bit. I'm going to try and write that same idea in other words that I think makes it a little bit more simple. So what this theorem is saying is that a line that's tangent to a circle will be perpendicular to the radius that's drawn out to the point of tangency. To me, that makes a little more sense. So let me write that out. A line perpendicular, oh, not perpendicular, I'm sorry, a line tangent to a circle, will be perpendicular to the radius that's drawn to the point of tangency. So in this picture here, since it tells us that line AB is tangent to circle C, then we would see that this, when we draw that radius out to the point of tangency, we're going to form a right angle right there. So angle CPB would be a right angle, and of course that would mean that angle CPA, this one here, would also be a right angle. Usually we only label one of those two as a right angle. But that's what this theorem is saying, that when we have this line that's tangent to a circle, and then we draw a radius that goes out to that line, to the point of tangency, we're going to make a right angle right there. And that theorem is another one that actually has a converse that is true also. So the converse of that theorem would say, well, if we have a line that's perpendicular to a radius at the end of that radius, right? So our line here, line AB, is perpendicular to the radius that comes out from C to the endpoint P. And then if that happens, then the line is going to be tangent to the circle, all right? So if we draw a radius out, and then there's a line that goes through the end point of that radius that's on the circle, and they end up being perpendicular to each other, the radius and the line that goes through that end point. If those are perpendicular, then that line has to be a tangent line, and that point would be the point of tangency for that situation. And again, that's just a converse of the last theorem. Basically, the idea is that when we have a radius coming out to a line that's tangent to a circle, they're going to be perpendicular to each other, or if they end up being perpendicular, then we know that the line is a tangent line. So we can put those to use in a couple ways. In our first example we have here, the question is asking, is this segment tangent to the circle? Now, so far we've talked about tangents being lines, but segments can be tangents as long as they would be if they were extended into a line, right? So segment KJ starts at K and ends at J. But if we imagine that it kept going past K and it kept going past J, if we kind of turned it into a line, if it still only intersected the circle in one spot, then we would consider that that segment is also tangent to the circle. So we're asking ourselves, is that going to happen here? Is this going to be tangent to the circle? And what we're going to use is we're going to use that converse that we learned just a second ago. That if this was perpendicular to this radius, we have a radius from the center of the circle coming out to point J, and if that makes a 90-degree angle right here, then we would be able to conclude that this is actually a tangent to the circle. So now the question is, how are we going to determine if that's a 90-degree angle? And of course, you'll notice that they also drew a segment that goes from P out to K, and that made a triangle here. And so some of you are probably already seeing what we're going to do. One way we could check to see if this is a 90-degree angle is we could check to see if the Pythagorean theorem would work for this triangle. It has a side that's 6, a side that's 9, and then this side here is 10 units long, because I could add the 4 and the 6 together to get 10 for this side. So if I can take the two shorter sides and use them as A and B in our Pythagorean theorem, and I can square them and add them together, and it equals the longest side squared, then we would be able to say that this is a right angle. So we're going to use 9 for the A, 6 for the B, and 10 for the C, and we're going to see if the Pythagorean theorem works out here. So I'll say, does 9 squared plus 6 squared, does that equal 10 squared? And 9 squared is 81, 6 squared is 36, and 10 squared is 100. If I add 81 and 36 together, I'm going to get 117, which does not equal 100. Therefore, I would say that line KJ is not tangent to circle C. The reason it's not tangent is because this is not going to be a right angle right here. So the idea would be, apparently, if I turned this into a line, it would intersect the circle at another point. In the picture, it doesn't look like that's going to happen, but the math tells us that that's what would happen, because the Pythagorean theorem doesn't work in this triangle. Now in this example, we are told that this is a tangent segment. Segment ST is tangent to our circle, and it asks us what's the radius of the circle then. You'll notice that it has x drawn as the radius length 2 times, one going from R out to S and one going from R out to this point that they didn't label, right? But since they're both a radius, they would have to be both equal to the same thing, or x, which we don't know. So what we're going to use here is the idea that if this is a tangent, then we know that that's a right angle right there, because that radius going out to the point of tangency would be perpendicular to the tangent. And if that's a right angle, then this is a right triangle here. And we should be able to, again, set up the Pythagorean theorem. A squared plus b squared equals c squared. Now, a and b are pretty clear what they're going to be. One of them will be x, and one of them will be 24. So I'm going to use x as the a and square it. I'll use 24 as b and square it, right? Because a and b are the legs of my right triangle. They're the parts that make the right angle. But then c here is going to be this entire side. So we have to ask ourselves for a second, what is the length of this side? And it would be x plus 18, because it would be this portion added to this portion. This portion's x, this portion's 18, so that entire segment is equal to x plus 18. So now we're going to say that equals x plus 18 quantity squared. So the next thing we need to do is simplify a little bit. There's not much I need to do with x squared, but I can take 24 and I can square it and get 576. And then now comes the tricky part, because now I need to simplify quantity x plus 18 squared. And a lot of people will try to just distribute that squared in and turn it into x squared plus 18 squared. But we can't do that, because what this is telling us is that I'm going to take the x plus 18 and I'm going to multiply it times x plus 18. And so you might remember back from Algebra 2, when I take this parentheses and multiply it times this parentheses, I have to multiply this x times both of these, and then I have to multiply this 18 times both of these, or you guys remember it as I need to FOIL this thing, right? I need to multiply the first terms together, the outside terms, the inside terms, and then the last terms together. So let's go ahead and do that. Nothing's going to change on the left side of my equation. And then when I multiply the first terms together, that's x times x, which is x squared. The outside terms is going to be x times 18, which I'll write as 18x. The inside terms is 18 times x. And then the last terms multiplied together is 18 times 18, which is going to be 324. And then I can simplify on the right side of my equation, because I can add the 18x and the 18x and get 36x. And then I have plus 324. Now at this point, some of you are realizing, wait a minute, I have x squared term and I have an x term. Does that mean I'm going to have to factor this to end up solving it? And a lot of times that's what's going to happen when you have an equation that has an x squared and an x that's not squared. A lot of times that means that you're going to have to use factoring or the quadratic formula if you've learned about that. But in this case, we're going to see that that's actually not going to be necessary. Because if I subtract x squared from each side, those x squared terms are going to go away. So let me just show you what I mean. If I subtract x squared on both sides, then what will happen is I'll have 576 equals 36x plus 324. And so you see now I no longer have an x squared term, so I can solve this in kind of what I would say is the easy way, where I'm just going to try and isolate that x, get it all by itself, by first subtracting 324 from both sides. So I'll do minus 324 on both sides. That's going to give me 252 equals 36x. And then I'm going to divide both sides by 36, and I'll get x equal to 7. And since x was representing our radius, there's our answer. Our answer is that the radius will be 7. So this problem, you can see, is a little bit of a little review from algebra, using a lot of algebra skills that you would have learned back in Algebra 1. But it all starts with using the idea that when that radius is drawn out to the point of tangency, it's going to form a 90-degree angle with the tangent line or the tangent segment. And since that's a 90-degree angle, this is a right triangle, and that can lead us towards using the Pythagorean theorem to set up an equation we can solve. Now here we have another example where it says that line M is tangent to our circle at point B, and line N is tangent to our circle at point C, what is the value of x right here, which would be the measure of this angle? Now, initially this seems like we don't have, like where do we even start on this problem? But then we always got to remember that every problem gives us clues, and we just got to think, why are the clues there, right? So if it tells us that line M is a tangent line, and then we have a radius that comes out from the center to B, that would mean that that's going to form a 90-degree angle there. And then the same thing's going to happen right here, right? That if line N is tangent and we have a radius coming out to that point of tangency, it's also going to make a 90-degree angle there. And then if you kind of isolate, if you kind of focus in on this shape right here, A, B, T, C, that's a quadrilateral. And we know that for quadrilaterals, all of their angles, when you add them together, should equal 360, right? All four-sided shapes, the sum of their angles inside the shapes should be 360. So that would mean that if I took x plus 135 plus 90 plus 90, I should get 360, right? The four angles in that shape are, x, 135, 90, and 90, so those added together should give me 360. So that means that x plus, let's see, 135 plus 90 plus 90, well, let's just do 135 plus 180, combine the two 90s. And then if we add 135 and 180, we're going to get, I think that's going to get me, let's see, 135 plus 180 will be 315. And then if I subtract 315 from both sides, then that gives me x equal to 45. So 45 degrees is our mystery angle right there. Now we have one more example that's going to use those two theorems that we learned about a few minutes ago. A little bit more complicated picture happening here, we see. First of all, we're asking, is line MP tangent to the circle N? Is this a tangent line? And so what do we know about what's happening with line MP? Well, we see that when I draw the radius out to M, and then I connect that center out to P, I make a 58-degree angle, and then there's a 33-degree angle right here. Now, if this was tangent, if line MP was tangent, then we know that this would have to be 90 degrees from the radius, the radius drawn from the center out to that point right there that might be the point of tangency. That would need to be 90 degrees for this to be a tangent line. So we can check if it would actually be 90 by looking at triangle NPM, right? This triangle right here from out to P, over to M, and then back to N, that would have to have a total of 180 degrees for its three angles. So let's add. Let's see. If I do 58 plus 33, that gives me 91 degrees. And then if I do 180 minus 91, I get 89 degrees. So that means that this angle right here would actually be 89 degrees and not 90. This would be 89 degrees. And that would tell me that no, this is not a tangent line for this circle because it didn't form a 90-degree angle with the radius. Therefore, line MP is not tangent to circle N. Now, part B says, if segment LK is tangent to circle N at L, what is the length of segment KN? Well, if this was tangent, then of course we know it's going to make a 90-degree angle there. And then we would have a right triangle. Triangle NLK would be a right triangle. So again, we can do the Pythagorean Theorem. We can say that a squared plus b squared equals c squared. The hypotenuse, or c, would be segment KN. Now, how long is segment KN? Well, segment KN is an x minus 1 portion plus a 9, right? So let's see, let's write it over here. KN is equal to x minus 1 plus 9, which would be x plus 8. Segment KN would have a length of x plus 8. So I know that's going to go where c is. So I know this is going to say x plus 8 squared. And in a minute, of course, we're going to kind of FOIL the x plus 8 times the x plus 8 to get what this is going to simplify out to. But first, we've got to think about a and b. Now a and b would be the legs. I can see that one of them is x plus 5. So let's use that as a. I'm going to have x plus 5. That's going to get squared. But then how long is this side right here? It doesn't give me anything, except for it does say that from n out to this point on the circle is 9 units long, which would tell me that the radius of my circle is 9. And since all radii would have that same length, that means that ln also has a length of 9. So I'll put a 9 squared right there in my Pythagorean theorem. Now I need to simplify. So I got to do x plus 5 times x plus 5 right here. And I'm going to have to do x plus 8 times x plus 8 right here. So let's go ahead and do that. When I FOIL the x plus 5 times the x plus 5, I'm going to have x squared plus 5x plus 5x plus 25. And then I'll have plus 81 for the 9 squared. And then over here I'll have x squared plus 8x plus 8x plus 64 for when I FOIL these two parentheses. So now we got a lot of cleaning up to do, right? We have some like terms to combine here and here. Then these two can be combined, and then these two can be combined. So I'm going to combine all those like terms. X squared plus 10x plus 106 equals x squared plus 16x plus 64. And then I might notice that I have an x squared on the left and I have an x squared on the right. So essentially those are going to disappear. They're going to kind of cancel each other out. So I'm just going to cross them out because if I subtract an x squared from each side, they'll both be gone. And that leaves me now with 10x plus 106 equals 16x plus 64. So I'm going to move these 10x's over to here. I'm going to move this 64 over to here. So I'm going to say minus 10x on both sides. And I'm also going to say minus 64 on both sides. So I'm kind of doing that all in one step. Cancel here. And I'll have a 42. And then over here, the 64s will cancel. And I'll have 6x. And if 42 equals 6x, that means x equals 42 divided by 6, which is 7. And we haven't answered our question yet, right? Because it asks not what is x equal to, but what is the length of kn. We already said that kn is x plus 8. So now we can say that kn is now 7 plus 8, which is 15.